Hello, I'm Dr. Harper. This video is in Supply Chain Analytics Logistics Homework Excel Tutorial, Company B, Part 2. So let's bring up the problem. Now in this problem, Company B, an international distribution company of containers with corporate offices in Manila, has been expanding warehouse operations in North American continent that service customers in the Asian continent over the past 4 years. Leanne Abel, VP of Logistics, has called a planning meeting to discuss possible modifications to shipping schedules because of recent changes in operations. The motivation for the meeting is changes in the demand at different destinations. So there's the part 2. The demand has changed. The unit cost of shipping from each source warehouse to each destination site, the capacity, the demand, etc., is given in the table. So when we look at this, we can see that 917.70, again Vancouver from part 1, has been expanded by 10% because they knew there's going to be some growth in the demand. So 900% plus the total capacity from the sources here in the North American continent is 1600. But right here we have 800. Here's 1800. Here's 5 and 510 and 810. So there's 1,820. So we're going to have more demand than capacity. And so the meeting is, what do we ship? So let's take this problem. And we've solved it before, but this time we're going to solve it with the new demand. So Control C, let's bring in Excel. Here it is. Let's come down here, ways, Control V. There we go. Okay. Let's make this larger so we can. Let's make this larger so we can see it. Full screen this. Okay. And so let's broaden this out. Let's level these off, and then let's level these off. And just format a little bit. There we go. Okay. So there's now notice our capacity. Let's just do a little bit of capacity here is going to be equals the sum of these two. And our demand equals the sum of these three. And notice our demand is greater than our capacity. Therefore, when we ship, it's going to be infeasible because you can't ship 1670 and meet a demand of 1820. So how do we handle this? Well, down here, this is the problem. Okay, so what we're going to be doing here is bring this demand down. 1, boom, and say, well, what's the difference? Well, it's going to be 1820 minus 1670 is 150. Okay, so let's have a dummy source over here. The cost is 0, and the capacity is 150. So now, when we ship, let's center this, and there we go. When we ship everything from our sources here to our destinations, then we will have our demand satisfied. But everything that the dummy ships is a virtual; it's not real, and that's the amount we cannot do. And so we have a back order or delay or ship the next shipment or whatever. So let's solve this thing. So here's the setup. So down here's a solution. Okay, so the schedule, and it's going to be the same up here. Tokyo, Shanghai, and Hong Kong. Let's put it here. And down here is same as this. Okay, but over here, this is what is going to be shipped. And down here, this is going to be received. Okay. And there we go. So now this right in, let's take all of this. Let's format this so we can see what we're doing. This right here is going to be our decision variables. Let's box that in and shade this in. There we go. And everything that's shipped is the sum from Los Angeles to the 3. Make sure we got it all. Yep. Copy this down. Copy, copy. And then everything that is received is the sum from Los Angeles, Vancouver, and the dummy. Make sure the dummy. Could have said Roger, but I said dummy. Okay. And then our total cost is the same as before. Some product of our unit costs up here, including the dummy, comma, the shipment, including the dummy. Okay, and there's our total costs. So then we just solve it. Okay, so we go to Solver now. This is our objective function. We want to minimize the cost by changing these variables, all of them. Add what is shipped is going to be less than or equal to the capacity. I could say equal because it's going to be equal. You're going to ship everything, but I'll say less than. And add everything that's received is greater than or equal to the demand. Again, I could have said equal to. I probably should have, but it doesn't matter because the greater than or equal to will converge. Okay. The greater than and less than will have least upper bound and greater lower bound, and it'll come and converge because we force it to converge because the same capacity is the same as the demand. Okay. We have unconstrained non-negativity constraints. We want a simplex algorithm because it's all linear. So you solve this thing, and there we go. Sure enough, solver found a solution. All constraints and optimality conditions are satisfied because it's all linear. We say OK, and there's our, let's just come to our data here, and let's make it dollars, currency. And there we are. There we have it. Okay. Well, that's pretty much all I had for this problem for Company B Part 2. I hope this helps. And between now and the next time I see you, I want to urge everyone to be safe and take care.